Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. Today we're going to investigate where is MH370. Independent Aircraft Investigations brings you the established facts. We provide traceability of all evidence to a source authority, and we make a clear distinction between factual data and analytical interpretation. If you find this analysis useful and want to see future independent investigations, then subscribing to the channel helps ensure this work continues. Aviation news is covered on daily airline news as it happens. This channel is reserved exclusively for in-depth investigations. The ATSB has searched underwater around 120,000 square kilometers of the southern Indian Ocean, from 40 degrees south to around 33 degrees south. And Ocean Infinity has searched underwater around 140,000 square kilometers, from 36 degrees south right up to 25 degrees south. Oliver Plunkett, the CEO of Ocean Infinity, said recently that if nothing else, we can say with confidence that it isn't where we looked. And that matters. It brings clarity, and it will help those continuing to study the evidence refine their thinking and shape future search strategies. So how should we refine our thinking and shape future search strategies? The fundamental question, where is MH370? Boeing published the maximum range of MH370 based on the fuel loaded for the flight. Inmarsat published the satellite data and determined that MH370 crashed within 120 nautical miles of the seventh arc. So why not look at the point where the maximum fuel range and the seventh arc intersect? That location is 39.3627 degrees south, 85.6648 degrees east. And it was one of the first places where we have looked. What if more fuel was loaded onto the aircraft than previously stated? What if the Boeing 777-200ER was loaded with fuel to its maximum capacity? MH370 could go just about anywhere in the world apart from Central and South America. And MH370 could go well beyond the Inmarsat 7th arc. So anywhere in Africa, Europe, Asia, North America, Australia, New Zealand, the Antarctica, the Arctic, Pacific Islands, you name it. The ACARS data sent from the aircraft at 17:07:29 UTC gives the total fuel weight remaining just after takeoff and every 5 minutes until the cruise altitude was reached. 49,200 kilo at takeoff, then 47,800 kilo 5 minutes later, then 46,500 kilo, 45,400 kilo, 44,500 kilo, and finally 43,800 kilo at 17:06:43 UTC at an altitude of 35,004 feet. And what if we ignore the Inmarsat data? And what if MH370 was like Helios Flight 522 and everyone on board suffered from critical hypoxia, resulting in a ghost flight? Well, the Defence Science and Technology Group in Australia has given us the answer. If MH370 simply continued in the same direction from the last known radar point, it would have crashed at around 21 degrees north, 55 degrees east, which is in the desert of Saudi Arabia and just over the border from Oman. The report by the Defence Science and Technology Group, DSTG, describes how Bayesian statistical methods were used to estimate the probable crash location of Malaysia Airlines Flight 370 in the southern Indian Ocean. Because the aircraft's precise trajectory after the last radar contact was unknown, DSTG combined limited observational evidence with a probabilistic modeling to estimate a posterior probability distribution of possible flight paths and final locations. The DSTG analysis identified the highest probability crash region along the southern part of the seventh arc, centered roughly near 38 degrees south, 88 degrees east. This probabilistic result informed the seabed search conducted by the ATSB, the Australian Transport Safety Bureau. The DSTG method does not produce a single flight path, but a probability distribution that reflects uncertainty in the aircraft trajectory, given the available evidence. And early trajectory studies conducted by Boeing explored a wide range of flight levels and ground speeds capable of satisfying the Inmarsat arc geometry. These analyses illustrate that multiple physically feasible trajectories exist prior to the imposition of probabilistic modeling assumptions. The DSTG analysis subsequently applied a Bayesian framework to identify a most probable crash region in the southern seventh arc. However, the resulting posterior distribution depends strongly on the assumed aircraft trajectory dynamics model. In the original DSTG model, the aircraft is assumed to cruise in one of a small set of prescribed guidance modes and does not change between these modes except for a single possible transition from LNAV to constant heading flight. And this restriction effectively constrains the post-radar trajectories to near constant track flight once the transition has occurred. In a new study, I examined the sensitivity of the DSTG Bayesian search framework for MH370 and the assumptions embedded in the aircraft trajectory dynamic model, showing that allowing a single LNAV direct to Waypoint event can substantially expand the range of seventh arc intersections consistent with the Inmarsat timing constraints. I've included a link to the study titled Trajectory Dynamic Sensitivity of the Bayesian Search Model for MH370. And this study examines the sensitivity of this distribution to one modeling assumption within the aircraft state transition model. The first section is the prior information. The model began with a prior distribution of aircraft states based on Malaysian military radar observations up to the final radar contact at approximately 1822 UTC, the Boeing aircraft performance limits, and plausible autopilot guidance modes. The 1822 radar observation was not used quantitatively because the latitude and longitude derived from it are likely to be less accurate at long range, and the aircraft may have maneuvered prior to 1822. Instead, a prior was defined at 1801 at the penultimate radar point. And then let's look at the measurement model. The analysis used satellite communication data from Inmarsat, specifically the burst timing offset, the BTO, which constrains the distance between the aircraft and satellite, and the burst frequency offset, the BFO, which provides the Doppler shift, indicating radial velocity. These measurements allowed investigators to infer which simulated trajectories were consistent with the recorded satellite signals. And thirdly, they have an aircraft dynamics model that defines possible aircraft trajectories after the last radar contact were generated using a stochastic state transition model representing aircraft motion under different guidance modes, for example, LNAV or constant heading or constant track. Because the aircraft trajectory between satellite measurements was unknown, this model was used to generate candidate trajectories consistent with the aircraft performance limits. Then DSTG used a particle filter. A large ensemble of candidate trajectories was simulated, and each trajectory was weighted according to how well its predicted BTO and BFO values matched the observed satellite data. This process produced a posterior probability distribution of flight paths. And then they included a final impact distribution, the distribution of aircraft states at the final satellite handshake at 0019 UTC on the 8th of March. And this was combined with an assumed descent model to estimate the probable crash location along the 7th satellite arc. In my new study, I retain the DSTG radar prior and the Inmarsat measurement model unchanged, and I examine only the sensitivity of the posterior search distribution to one modeling choice within the aircraft state evolution law. Our modification does not alter the prior or the measurement model. Instead, it replaces the above constraint with a more general guidance model in which a single commanded route change is permitted during autopilot flight. Thus, all candidate trajectories generated under the modified dynamics must remain consistent with the full sequence of Inmarsat BTO and BFO measurements. Accordingly, the only modification relative to the original DSTG framework is the introduction of a single LNAV direct-to-waypoint event within the state transition law governing aircraft dynamics. The constrained DSTG solution space is ultimately defined by the 7th arc, and any candidate trajectory generated under the modified dynamics must intersect the 7th arc at the time of the final satellite handshake. We're showing a figure which illustrates the DSTG prior solution space when the Inmarsat measurements are not applied. The distribution is centered around 21 degrees north, 55 degrees east, demonstrating that the satellite measurements are essential for constraining the final trajectory to the southern Indian Ocean. Now let's have a look at the waypoint candidates. And in principle, the candidate waypoint set should be the set of named navigation fixes available in the Boeing 777-200ER flight management system installed on the aircraft 9M MRO at the time of the accident. And in the absence of the exact aircraft navigation database, this study used all named aeronautical waypoints within the DSTG southbound solution space as a proxy for the navigation fixes available to the aircraft. To minimize confirmation bias, No waypoint is selected on the basis of its effect on the posterior distribution. Instead, a candidate set of named aeronautical waypoints is defined in advance using only geometric criteria that identify the southbound solution space. Each waypoint in the eligible set is assigned equal prior probability. The map shows the aeronautical waypoint set within the DSTG southbound solution space, includes fixes such as Elati, Pipoff, Mutmi, Babin, Runnet, Dubag, Polam, Ikasa, and Sinam, as well as others. The red diamond marks the DSTG prior, located on the penultimate radar point over the Malacca Strait. The curved lines are the Inmarsat arcs, with the southern arcs corresponding to the later satellite handshakes leading to the seventh arc at 001929 UTC. A waypoint is considered eligible only if a trajectory executing a direct-to command toward that waypoint can still intersect the seventh arc at the time of the final satellite handshake. Waypoints that cannot satisfy this terminal constraint are excluded from the candidate set. Although the route dynamics are relaxed, the measurement model is unchanged. Consequently, all candidate trajectories must remain consistent with the full sequence of Inmarsat BTO BFO constraints, including the seventh arc positions at their respective handshake times. The modified state transition model introduces a single LNAV direct-to waypoint event. To avoid subjective waypoint selection, the eligible waypoint set is defined deterministically. This set includes every aeronautical waypoint within the region in which trajectories consistent with the Inmarsat arc measurements can plausibly evolve toward the southern Indian Ocean. No waypoint is excluded or preferentially selected. All waypoints are therefore assigned equal prior probability. This ensures that every aeronautical waypoint within the DSTG southbound solution space is treated equally in the modified state transition model. In addition to the waypoint variable, the model introduced a latent event time, T, representing the time at which the aircraft executes this direct-to command. And the event time is restricted to a discrete set of candidate times at 15-minute intervals between 1900 UTC and 2400 UTC, covering the period of sustained southbound flight following the final radar observation. These times are assigned equal prior probability. And for each combination of a waypoint W and event time T, candidate trajectories are generated using the modified state transition model described previously. And these trajectories are then evaluated using the unchanged Inmarsat BTO and BFO measurement likelihoods. Consequently, all simulated trajectories remain constrained by the full sequence of 7 Inmarsat arc measurements at their respective handshake times. For the purpose of constructing a representative baseline trajectory, the study used the illustrative geometry described by the DSTG at the second arc, 1941-03 UTC, near 1.0 degrees south, 93.6 degrees east, at an assumed altitude of 30,000 feet. A flight path to 38.0 degrees south and 88 degrees east at 001929 UTC lasts 4 hours, 38 minutes, and 26 seconds, and covers a distance of 2,233.7 nautical miles. That's 4,136.9 kilometers, on a track of 187.3254 degrees true. And this implies an average ground speed of 481.343 knots. And based on the assumed ground speed, we can plot the position of MH370 between the 7th of March 2014 at 1900 and the 8th of March 2014 at midnight. The map shows the DSTG flight route with hourly markers from 1900 to 2400. The distance to go, the DTG, to the Inmarsat 7th arc is estimated at each hourly interval between 1900 and 2400 and is shown in the table. And the DTG reduces from 2,563 nautical miles at 1900 to 156.3 nautical miles at 2400. Between 1900 and 2200, the 7th arc between 10 degrees south and 38 degrees south remains reachable. We are showing the reducing range of possibilities between 1900 and 2400. By approximately 2300, the remaining reachable aeronautical waypoints require significant deviation from the southbound trajectory. The 3 waypoint examples illustrate that the range of possible 7th arc intersections depends strongly on the geometry of the commanded waypoint. Waypoints located further west of the baseline trajectory produce larger timing variations and correspondingly wider latitude intervals along the arc. We're showing the range of possible trajectories resulting from a single LNAV direct-to command toward waypoint Pollen, executed between 2000 and 2230. Earlier diversion times produce a wider range of possible intersections with the 7th arc, while later diversion times become increasingly constrained. After approximately 2230 UTC, trajectories via Pollen can no longer intersect the 7th arc at the time of the final satellite handshake under the baseline cruise speed assumption. There is only one solution between 2215 and 2230 UTC that satisfies the 7th Inmarsat arc final handshake timing constraint without further change in speed or route. The results presented here have implications for the interpretation of previous seabed search efforts. The primary underwater search conducted between 2014 and 2017 by the ATSB, informed by the DSTG Bayesian analysis, focused on a region of the southern Indian Ocean centered approximately near 38 degrees south. Subsequent search activities by Ocean Infinity have also concentrated on portions of the southern arc in the vicinity of this region. The sensitivity analysis presented in this study suggests that the latitude of the 7th arc intersection can vary under modest changes to the aircraft dynamics model, while remaining consistent with the Inmarsat timing constraints. The purpose of the present work is not to redefine the most likely crash location, but rather to illustrate that set of trajectories compatible with the available measurements depends in part on modeling assumptions within the trajectory dynamics. As such, the interpretation of posterior search regions derived from the DSTG framework should be considered in light of these underlying assumptions. For illustrative purposes, trajectories are propagated assuming constant ground speed following the waypoint diversion, consistent with the speed ranges considered in previous performance analyses. The Pollum example reveals a stronger effect than simply broadening the seventh arc latitude interval. Allowing a single LNAV direct to waypoint event introduces a time-dependent feasibility boundary. Early diversion times admit a wide range of arc intersections. Intermediate diversion times admit a progressively narrower interval, and late diversion times become incompatible with the final handshake under the baseline cruise speed assumption. This indicates that the inferred posterior search region depends not only on the geometry of the permitted maneuver, but also on the temporal window within which such a maneuver is allowed by the aircraft dynamics model. The diversion examples also reveal an asymmetry in the reachable arc latitude interval. While waypoint diversions can significantly expand the range of the northern arc intersections, the southern bound remains close to the baseline southbound trajectory. This occurs because the baseline trajectory already approximates a time-efficient southbound path towards the seventh arc, whereas lateral diversions primarily delay southward progress. In Bayesian search problems, the posterior distribution depends jointly on the prior, the measurement model, and the assumed state transition dynamics. While the DSTG analysis carefully evaluated uncertainties in the measurement model and prior, the sensitivity of the posterior to alternative but plausible trajectory dynamic assumptions has received less attention. The diversion examples reveal that the feasible trajectory set forms a wedge-shaped region along the seventh arc. The southern boundary remains anchored near the baseline southbound trajectory. This occurs because the fixed timing of the final satellite handshake progressively constrains late diversions toward the time-efficient southbound path. The present study examines this sensitivity by introducing a minimal modification to the state transition model while leaving the prior and the measurement model unchanged. And this behavior illustrates how time constraints in trajectory models can induce structured regions of feasible solutions even when only minimal modifications are introduced to the underlying state transition dynamics. Under a near constant heading or near constant track southbound assumption, the sequence of timed Inmarsat arc constraints tends to compress the feasible trajectory family into a narrow southern corridor. Allowing a waypoint-based LNAV direction breaks this conversion by introducing lateral displacement and timing variation, thereby expanding the set of reachable seventh arc intersections. Early trajectory studies conducted by Boeing explored a wide range of flight levels and ground speeds capable of satisfying the Inmarsat arc geometry. These analyses illustrate that multiple physically feasible trajectories exist prior to the imposition of probabilistic modeling assumptions. So, in summary, Boeing demonstrated that many physically feasible flight paths can satisfy the Inmarsat arc geometry. And the DSG analysis subsequently applied a Bayesian framework to identify a most probable crash region along the seventh arc. However, the resulting posterior distribution depends strongly on the assumed aircraft trajectory dynamics model. The three waypoints we've shown as illustration, waypoint Polum, Icasa, and Sinam, show that the reachable latitude interval along the seventh arc depends strongly on the geometry of the commanded waypoint. Waypoints located significantly east or west of the baseline southbound trajectory introduce larger timing variations and produce wider latitude intervals. Waypoints located closer to the baseline trajectory result in smaller variations. The modified Bayesian model introduces a single waypoint event to demonstrate the sensitivity of the trajectory space while maintaining minimal deviation from the original DSTG framework. Even very small changes to the route dynamic assumption can significantly alter the posterior search region derived from the same Inmarsat measurements. In conclusion, the Bayesian search framework developed by the DSTG provided the first rigorous probabilistic analysis of the final trajectory of MH370. And that analysis, combined with a radar-derived prior, the Inmarsat BTO and BFO measurements, and a stochastic aircraft dynamics model, to estimate the distribution of possible crash locations along the southern part of the 7 Inmarsat arc. Illustrative trajectory propagations demonstrate that allowing a single waypoint event can significantly expand the range of trajectories that remain consistent with the timing constraints from the Inmarsat arcs. These results highlight that the inferred crash region derived from the DSTG framework is sensitive to assumptions embedded in the aircraft dynamics model. The analysis presented here does not attempt to determine the most likely flight path or crash location. Further investigation using the full DSTG particle filter framework with relaxed trajectory dynamics may provide additional insight into the sensitivity of the posterior crash distribution to assumptions embedded in the aircraft dynamics model. MH370 is conceivably within 100 nautical miles of the seventh arc between 38 degrees south and 18 degrees south, which is an area of 500,000 square kilometers. And we've already searched 260,000 square kilometers. So we've covered just over half of the conceivable underwater search area. The Whisper search area is 3,000 square kilometers, and that would take 5 days to search with 3 AUVs. At 29 degrees south and 100 degrees east, the Whisper area is up to 45 nautical miles from the seventh arc. To complete the whole seventh arc up to 45 nautical miles to the southeast, from 38 degrees south all the way up to 25 degrees south, is a total of 40,000 square kilometers. And that would take around 70 days with 3 AUVs. So in conclusion, the study shows that there is more work to be done in order to complete a thorough search of the seventh arc area. Thank you very much for joining me today. I hope you found this study interesting, and a link to the study can be found in the description below and on my website, mh370search.com.